everybody, welcome back to Mathematical Statistics. We were talking about method of moments estimators, which were estimators for parameters, a general theta, an alpha, a beta, a mu, a lambda, a sigma squared, a lowercase gamma, and a Pareto distribution. We were estimating these by equating sample moments with distribution moments, those theoretical quantities with those sample quantities, and solving for the unknown parameter and putting a hat on it. And we like method of moments estimators because they're highly intuitive like that, and they tend to be easy to find. And other reasons we like method of moments estimators is that we can show that they are usually, given some conditions on things, they are usually consistent estimators of the unknown parameter, which means they usually converge in probability to the thing you're trying to estimate. You can imagine getting this result from the weak law of large numbers, which says that the first sample moment x bar always converges in probability to the first distribution moment mu, and the second sample moment, 1 over n, the sum of the xi squareds, is just an x bar for the data set that's all been squared. So that's actually the weak law of large numbers can be applied there, and that would converge in probability to the second non-central moment. And when we throw them together in some kind of maybe more complicated function, if that function was a continuous function of, say, the first and second moments, then we could use the continuous mapping theorem in addition to the weak law of large numbers to get convergence in probability of our method of moments estimators to the unknown parameter or parameters. And we can even get that if the g function, the continuous function that you're trying to put things through, is not exactly continuous, but has some nice smoothness properties in certain regions. So again, we like method of moments because they're easy to find, because they're highly intuitive, they're often consistent, meaning convergence in probability, and they are often asymptotically normal. Now, why is this important? Because let me get my screen going here. Not all parameters have a nice common sense estimator. Up until now, we have not had a real method of estimation. We've just done things that have sort of felt right. Like if you're trying to estimate the mean of the distribution, use the mean of the sample. But there are many distributions where it's not going to feel so obvious, like a gamma distribution with shape parameter alpha and inverse scale parameter beta in our parameterization of the gamma distribution. Some people parameterize it differently, and beta is known as a scale parameter. We came up with method of moments estimators last time, and we got the method of moments estimator for alpha was x bar squared over 1 over n, the sum of the xi squared minus x bar squared. Now, who would have guessed that? That doesn't seem like a common sense, feel good, come on, can't you guess that kind of estimator? But it did come from the common sense, feel good ideas of equating moments. And before I go any further, let me just write down the beta method of moments estimator. It was the same thing except the numerator was not squared. So what if you had a gamma distribution and you were doing a hypothesis test, say concerning alpha, that alpha was equal to 1 versus the alternative that alpha was not equal to 1, restricted to the parameter space that does say that alpha has to be positive. So step 1 is to choose a statistic, which tends to be an estimator of the thing, but is really any statistic that you can go forward and work with. If you are making a hypothesis test concerning alpha, what statistic would you use? We don't really have an intuitive, feel-good, common sense estimator, so we might use this as the chosen statistic for step 1. And then in step 2, we would write down the form of the test, but in step 3, we would have to come up with the cutoffs that we use in the form of the test, like saying that this is greater than C and less than D. And to do that, we need to know how to work with this statistic. So if you can find, using our transformation methods from the very beginning of this course with Jacobians and G-inverse formulas, if you can find the exact distribution of this statistic, then you can find exact critical values for your hypothesis test. But if not, if we know that method of moments estimators are asymptotically normal, then we can still do a hypothesis test approximately in the large sample case by saying, I have a large sample and I'm going to treat this as approximately normal with some mean and some variance. So that's why we care about knowing asymptotic distributions of things. We always like to do things exactly and for finite samples, but if we can't, we'll go for the large sample approximations. So to sum it up, and I'm not proving these claims about consistency. We talked a little bit about why that's true with the weak law of large numbers and then putting that through continuous functions. I'm not going to prove these properties here. In our next method of estimation, which is coming up in just a few minutes, I'm going to prove all the details. Um, and I'm going to prove all the details in our third method. But method of moments estimators do have a lot of drawbacks, and I don't use them that often personally. So again, pros, intuitive, generally easy to find, often asymptotically consistent, meaning they converge in probability to the right thing under some mild conditions on what's going on with your distribution and the functions you're putting them through. Often asymptotically normal, which is a great thing for doing any sort of statistics like building a confidence interval or, as we were just saying, hypothesis testing. These things are great, but there are cons. They are biased for one. We saw in all our examples in the last class, we had biased estimators. We didn't check that, but they all were biased estimators. Um, they are often not uniquely defined, and that's not really a mathematical statement of is it well defined? That's a statement of the statistics community getting their act together and deciding on one definition. For example, we used non-central moments, but some people will use central moments and call them method of moments estimators. Or if people all agree on non-central moments, when we found the method of moments estimator for the lambda for the exponential distribution, we equated the first distribution moment with the first sample moment, solved for the unknown parameter, and put a hat on it. But we could have equated the third moment for the distribution and the third moment for the sample, solved for the unknown parameter, and put a hat on it. And that's also a method of moments estimator that's going to be different from the other one when we looked at first moments. Um, there are other things that are known as method of moments estimators that happen when people use any sort of sample versions of what they're trying to estimate, like plugging in a sample variance for a true variance, things like that. So method of moments estimation is not really well defined, um, although we could fix that part. We could decide on our definition and we wouldn't have that problem. But they may not even exist. A lot of distributions do not have any finite moments. Uh, our PDFs have to integrate to one, or in the discrete case, have to sum to one, but they might have they might have really heavy tails. They might not go down fast enough so that if you multiply the PDF by an X and then try to integrate it, that could actually blow up. And if that blows up, multiplying by X squared will also blow up. And so we won't have any moments, population or distribution moments existing for us to equate. So that's going to be a serious problem. And you can see in your table of distributions, you can go down the mean list and see some that say does not exist. And as another con is that method of moments estimators can actually produce values that are outside of the parameter space. Like suppose you have a parameter theta for your distribution and it takes on values from 0 to infinity. And based on the particular distribution, you compute a method of moments estimator. It's possible you get a negative value, but that's not in the parameter space. So that sounds really bad. So there are a lot of cons. Okay, so the cons I've just listed are usually biased, not uniquely defined, often don't exist. They may not be in the parameter space. And I don't know, I could probably think of a few more if pressed, but they're not the favorite estimator in the statistical community. But if you have nothing else, they're certainly great. And our next method of estimation requires us to maximize something, which we're going to do with calculus. But if the maximization is too messy and we have to do it numerically, doing some kind of gradient ascent method maybe, then we need a good starting point. Method of moments estimators often are good starting points for finding other types of estimators because you want something that has some bearing on the problem, not just a totally random starting point. So I don't mean to talk badly about them, but personally, I don't use method of moments estimators all that often. let's talk about the next type of estimators called maximum likelihood estimators. Now, I said that we were going to talk mainly about three types of estimators. One, method of moments. Two, maximum likelihood. And three, the UMVU, the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. Now, UMVUs sound really good, and they are just as good as they sound, but they can be hard to find and they might not exist. So I just wanted to let you know that maximum likelihood estimators, I think, are the most important. This is the most important method of estimation one needs to know in statistics. These are the workhorse estimators in statistics. They get used all the time. They are well defined. They have great properties. They're generally easy to find. And we're going to spend a lot more time on these than we did on method of moments estimators. So an acronym, we've got MLEs, and no one disagrees with that. I gave you a couple of possible acronyms for method of moments. But the idea is to look at the data. Now, data for us is the random sample, x1 out through xn. And then we want to choose the value in the parameter space that makes this data most likely to appear. That is the informal idea, and we're going to formalize it. I'm going to start with a hopefully motivating but oversimplified example, and then we'll kick it up to more realistic examples today. So we won't stay in the oversimplified case for too long. So we are going to flip a coin, and it's possibly unfair. So I'm gonna, flip a possibly unfair coin. So I'm going to let lowercase p be the probability of getting heads on any one flip. Now, in general, p takes on values between 0 and 1 inclusive. That is the parameter space. But in my oversimplified example, the parameter space, the values that p can take on, I'm going to limit it and say that p has to come out of the set 0.2, 0.3, or 0.8. So suppose you flip the coin a bunch of times and you get heads, tails, heads, 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 tails, heads, 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 something like that. Then, given this is the data you're looking at, which value from the parameter space do you think is most likely the value of p? So really, roughly and informally, it looks like we're getting a lot of heads. So I think that we have a high probability of getting heads. So this value of 0.8 seems most likely. And I would give that as my maximum likelihood estimate for P if I saw this data. Let's generalize this. And so I'm going to simplify it just a little bit more as I start the generalization, but then we will take away all these simplifications really soon. So just a little more formally. Oh, actually, let me go back here. What if your data consisted of just two flips and you got heads, heads? Now, which of these is most likely? Given I'm looking at heads, heads, I think that heads is coming up a lot. I don't have strong evidence for it because I have very little data. But given that that's what I'm looking at, I think I'm going to go with 0.8 again. Whereas if I were to see tails, tails, I think I'm going to go with 0.2 as more likely than the 0.8. So that's all the informal stuff. But formally, let's flip it twice. And let's suppose we have x1, x2, IID Bernoulli with parameter P. So I'm actually going to say, I'm going to flip the coin, and if I get heads, I'll assign a 1, and if I get tails, I'll assign a 0. So now we're talking about a nice known distribution with 1s and 0s. And the parameter is P, and let's continue to believe that the parameter space is 0.2, 0.3, or 0.8. And so I have 2 flips. Let's look at the probability of getting, what can we get? We can get 0 and 0, 0 and 1, 1 and 0, or 1 and 1. And the parameter P is one of these values. So I'm going to make a little table here. P can take on one of these 3 values. And then let's look at what our quote unquote data could be. So x1 and x2, I'm going to draw a lowercase x1 and x2 because I'm labeling actual realizations of the data, actual observations. There are the 4 possibilities. And so what is the probability of us seeing 0, 0 if the parameter is actually 0.2? That's what I want to put in here. So I want to fill this table with probabilities of seeing these various things under these various conditions. So I'm just going to write out a couple and then leave the rest to you. But this is the tails situation, right? So if I get a 1 with probability P, I get a 0 with probability 1 minus P. And so I get 0, 0 with probability 1 minus P, 1 minus P. And if P is 0.2, then that is 0.8 times 0.8, and we get 0.64. If P is 3, then this is 0.7 times 0.7, so I get 0.49. And if P is 8, then this is 0.2 times 0.2, or 0.04. If I go to this column, I get 0 and 1 with probability 1 minus P times P. So if P is 0.2, I get 0.8 times 0.2, which is 0.16, and so on. So let me finish out this column. This is going to be 0.21 and 0.16. The next column is going to be identical because instead of 1 minus P times P, we would have P times 1 minus P, same thing. So 0.16, 0.21, and 0.16. And the final column is going to be 0.04, 0.09, and 0.64. So here are possible values for your data. When we give an estimator, we don't have the data yet. If we do, then we have an estimate, not an estimator. So we're still, we don't know what's coming out for x1 and x2. So the maximum likelihood estimator for P is, I am going to call this P hat. And if you want, P hat sub MLE, but unless you're working with multiple estimators in a single problem or a single paper or report, then you don't have to put the subscript on it. But based on seeing the data, what is the value of P that gives you the highest probability of seeing the data? So if I see 0, 0, the highest probability is right here out of the column of probabilities, and that comes from this value. So my P hat is going to be 0.2 if x1 and x2 is equal to 0, 0. If I look at the next column of data, the highest probability, which is the highest of the 3 numbers in here, is the 0.21, and it comes from a P of 0.3. And that is going to be my maximum likelihood estimator if x1, x2 is 0, 1, or 1, 0. And finally, if I have my data being 1, 1, the highest probability here happens when P is 0.8. So I am going to get 0.8 to be the value that gives me the highest probability of seeing the data if the data is 1, 1. So this is a maximum likelihood estimator. And if you make all of these guys capital, then it actually looks like an estimator, like a random variable, because it's a little weird. These aren't random, but they're defined over random regions, if that makes sense. That's all there is to it. Now, what have we put in this table? The entries here are our joint probabilities. And our notation for this would be like f of x1, x2, semicolon p. And we are going to work with this joint PDF, even if we're working with continuous random variables where the joint PDF doesn't exactly represent probability, but it represents some kind of surface in a higher dimension under which some kind of higher dimensional volume represents probability. Okay, so let's try to generalize this. Suppose we have data, capital X1 through capital XN. These for us are almost always going to be IID, but they don't have to. So they're going to have a joint PDF, probability density function, f of x1 through xn, and then a semicolon, and then we write the parameter, which could be vector valued itself. If things are discrete, in the discrete case, this is going to be a joint probability. But if things are continuous, we're still going to start with a joint PDF as the kind of analog of the joint probability, even though it's then an n-dimensional surface under which volume represents probability. So this may not actually represent probability, but something closely related, something that's defining probability for us. And I want to write, because we're going to write this a lot, I want to write x as a vector. And again, theta could be a vector. I'm not being consistent with my vector notation, but I don't know. I don't want one-dimensional vectors either. So theta is a scalar or vector value thing. And if you want to put an arrow over it, that's fine. But in what we're about to do, we're not assuming it's discrete. However, if it was discrete, this is again the probability that capital X1 is equal to little x1 out through capital Xn is equal to little xn. And we want to maximize this probability as a function of theta. We want to think of the data, the x1 through xn, as fixed and given and observed, and then we maximize this probability as a function of theta. And if we're dealing with a continuous distribution, the maximum likelihood estimator is defined to be the theta that maximizes this joint PDF. Even though it doesn't exactly mean probability, it is an n-dimensional surface under which volume represents probability. So in either case, we want to maximize this as a function of theta. And you are going to be restricted to the appropriate underlying parameter space. If these are IID, as they always are for us, then this joint PDF is going to come by multiplying the same individual PDF with an x1 plugged in and an x2 plugged in out through an xn plugged in. But a maximum likelihood estimator could start with a more general joint PDF that is not necessarily a product of identical looking PDFs. Okay, so if we're going to maximize this as a function of theta, we're thinking of the data as fixed and given, and you might even say constant. And you're looking at the joint PDF as a function of theta. So let's switch up the notation a little bit and define a function known as a likelihood function. We're going to call it capital L of theta. That's going to be our notation for a likelihood function. And this is any function, so it's not going to be unique, proportional to the joint PDF. We'll have so many examples. When the joint PDF is thought of as a function of theta. If that doesn't make sense, by the end of today, it will definitely make sense. We're going to see a lot of examples that I think are really clarifying. But if you look at the joint, so there's also x's in there, but the notation is suppressed. And if you look at a graph of a likelihood as a function of theta, we want to find the value, if it exists and if it is unique, that maximizes the PDF. So theta hat is going to be the maximizer. If you're more mathy, you would say the argmax, the maximizer of L of theta, if it exists and if it's unique, and we need to talk about that. We'll get there. Before trying to find an MLE, I just wanted to point out that if I were to take my function and multiply by 3, then in my picture, it appears that when theta is 0, my likelihood is 0, and 3 times that would still be 0. But it would increase and decrease and whatever, the maximum would occur in the same place. So you can you can multiply your likelihood by any constant and then maximize that. And that's still how you would find the MLE. So 3 here is a constant. But in this scenario where we're thinking of the data as fixed and constant, note that here, again in this setup, something like the product as I goes from 1 to n of the xi is constant when thinking of the likelihood as a function of theta. So I probably am not going to be multiplying my likelihood by a constant, but instead dropping things that are constant. And this could include constants that actually look like numbers, and this could include things multiplicative constants involving the x's only. And again, if that does not make sense, it will by the end of today for sure, given all the examples we're going to do. One more trick before we go on. In finding MLEs, it is often going to be convenient to maximize not the likelihood directly, the so-called log likelihood. This is going to be the log of the likelihood. I'm going to denote it with a lowercase kind of script looking L. And this is going to be the log of the likelihood. That's my natural log. You can use a not natural log. And you could not use curly letters, but this is going to be my notation that I'm going to use in here for the log of the likelihood. Now, if you take the log of, if you look at this graph and look at the original white function there, if you take the log, that is going to change the shape of this thing. But because log is an increasing function, that's through here at 1, it is going to maintain the order of things. So if the value of the likelihood at one number is greater than the value of the likelihood at another number, then that's still going to be true after you take the log, and vice versa. If one is smaller, it's going to maintain the order. It's going to change the shape, but it's going to maintain the order, which means the highest value of the log likelihood is going to occur at the same place as the highest value of the likelihood. And this means instead of maximizing the likelihood function, you could maximize the log of the likelihood, and that is very often a much more convenient thing to work with. We're going to do it so much, in fact, that you're going to start thinking that taking the log of the likelihood is one of the steps in maximum likelihood estimation. But one day, it actually won't make things easier. It'll make things harder. So keep that in the back of your head. Taking the log is not a necessary step unless it makes things easier. And it almost always does. Let's do the coin flipping example, but I want to generalize it to flipping n times, not just 2 times. And I want to open up the parameter space to say that P is all values between 0 and 1 inclusive. So let's do it. Okay, suppose I have x1 through xn, IID Bernoulli with parameter P. parameter space for P is that P is between 0 and 1 inclusive. Let's find the maximum likelihood estimator for P. I did write the, not an, because it's going to be unique and it's often going to be unique. Today, I'm just going to focus on computation and finding maximum likelihood estimators, but eventually we're going to do the theory about when they're going to be existing and unique and consistent and unbiased or asymptotically unbiased or asymptotically normal, all that good stuff. Let's just do this problem. It's pretty formulaic. There's a recipe. I would write down the PDF that we're working with. F of x and p is p to the x, 1 minus p to the 1 minus x, and it lives on the space, the discrete set x can take on the value 0 or 1. From that, I can get a joint PDF. We're calling this f of the vector x and p. And because what we're working with, they're IID, this is a product of this PDF over and over again, but with different x's plugged in. So I don't get that PDF to the nth power, but I get f of xi and p. And so let's fill that in. This is the product as I goes from 1 to n of p xi raised to the xi, 1 minus p to the 1 minus xi, and an indicator that says that xi has to be in this discrete set. Note the brackets and not, note the curly brackets and not square brackets or parentheses. So let's multiply this out. This is p to the sum as I goes from 1 to n of the xi, 1 minus p to the n minus the sum of the xi. And so write that out slowly if you need to. Do it for n equals 2. And then a product of indicators. Here's another place in MathStat that I really like to use indicators because it is relevant that this indicator is constant when looking at this whole thing as a function of P. Like if there was a 3 out front and I wanted to define a likelihood, I could drop the 3. Similarly, I can and will drop this product of indicators. So A, not the, likelihood, because maybe someone else didn't drop them or someone else multiplied by 12. A likelihood is L, capital L of P, P to the sum of the xi, 1 minus P, n minus the sum of the xi. This is constant as a function of P. So the goal is to maximize this with respect to P. And you do this any way you can do it. But as I mentioned earlier, it's almost always easier to look at the log of this. So let's try that here. The log likelihood is like this lowercase sort of script L. This is going to be the log of the likelihood. And when you take the log through here, this product is going to become a sum, and the exponents are going to come down. So we get the sum of the xi times the log of p plus n minus the sum of xi times the log of 1 minus p. And I wrote theta. I guess I could keep it and say, well, that's our generic parameter, but I really did mean to write a p in there. I want to maximize it, so let's take a derivative with respect to p. This is a constant. The derivative of the log of p is 1 over p, so we get the sum of the xi, 1 over p, and then the derivative of this is the derivative of the inside, which is a negative 1, over the thing itself. So I get plus n minus the sum of the xi, then negative 1 over 1 minus p. Let me just rewrite this like fractions and put the negative over there. To maximize it, we're looking for a critical value. So I'm going to set this equal to 0. And then what I tend to do for expressions like this is not try to get a common denominator, but multiply through by a common denominator. If I multiply both sides by p1 minus p, I still get 0 on the right-hand side. And on the left side, I get some cancellation. So I get 1 minus p times the sum of the x's minus p times n minus the sum of the x's equals 0. And if we multiply this out, we get the sum of the x's minus p, sum of the x's minus np plus p, sum of the x's equals 0. And we do get some cancellation. And when you take the remaining part and solve for p, you're done. Make everything capital and then put a hat on it. We get the maximum likelihood estimator for p is p hat equals the sum as I goes from 1 to n of the capital Xi. Everything was lowercase there. We were just writing down a joint PDF and going through some algebra or calculus, divided by n, which is X bar. That is the maximum likelihood estimator for the parameter p for a Bernoulli distribution. And so if you want to estimate it, you average all your x's. And this makes a lot of sense because the Bernoulli gives you, for your x's, ones and zeros. And p is supposed to be the probability you get a 1. So what if your data looked like 0, 1, 1, 0, 0, 1, 0, 1, and so 1, 2, 3, 4, 5, 6, 7, 8. In this picture, n is 8, or in this list, n is 8. How would you estimate the probability you get a 1? It would naturally be, like 4 out of 8, given this data, which is actually the sample mean of this. But we're still talking about it before we have the sample when it's random. We're saying someone go take the sample and then compute the sample mean and come back with a number. But we're giving an estimator before they do that so that we can compare various estimators and say, with this probability, this estimator is going to be closer than this one, or we can still talk about probability. So there's our first MLE, and you should check that you did actually maximize the likelihood. What did I do? I took a derivative and I set it equal to 0. So that could be a saddle point or a minimum. And I am not going to try to trick you in this class. You should check this for completeness, but it's okay if you don't. Everything that you're going to solve for this class, you are actually going to be maximizing. But if you wanted to go back up here and take another derivative, then, well, you could show that you're going to get something negative when you plug in our MLE, which means you have something that's concave down, which means you are talking about a maximum. So in your research and in real life, you should definitely check that you didn't minimize things. But I claim we actually maximized it here, and we sort of always will be. If you find multiple critical values, then you should definitely be more careful. And again, if this is for your research, for your journal article, for your job, definitely check that you did maximize the function with a second derivative. Okay, let's do another example. In this example, let's go to the exponential distribution, which we use so often. Suppose these are IID exponential with rate lambda. Let's find the maximum likelihood estimator for lambda. Very formulaic. Write down the PDF. F of x and lambda, if you parameterize it according to a rate parameter, is lambda e to the minus lambda x, and an indicator saying that x takes on the value from 0 to infinity. So the joint PDF, f of x with a vector, is, because these are IID, is a product as I goes from 1 to n of the individual or a single PDF, but with different values plugged in. So this is going to be the product as I goes from 1 to n of lambda e to the minus lambda xi and an indicator. Could you leave these off? Yes, but you'll have to be careful, and you'll see that in not the next example, but the one after that. You'll see why I leave the indicator in. If you multiply this out, you get lambda to the n e to the minus lambda times the sum as I goes from 1 to n of the xi times a product as I goes from 1 to n of this indicator or these indicators. Okay, let's define a likelihood. We're calling this capital L of lambda, and we're dropping any multiplicative constants with respect to lambda. Again, sometimes there'll be a more obvious constant like 18 or 18 to the n because our sample size is always known. If that was there, we could drop it. Here, the only thing that is constant with respect to lambda and a multiplicative constant is this indicator. So I'm going to drop that, and we're left with lambda to the n e to the minus lambda sum of the xi. Next, I'm going to look at the log likelihood. Why am I doing that? And why did I do it in the previous example? You're going to do this a lot. You're going to do this, dare I say, most of the time, but it's not necessary. Your goal is to maximize this any way you can, and it almost always makes things easier because it brings exponents down onto one line. So in the previous example, there wasn't even an e in the problem, but I took the natural log, or you can use any base log. And even though there wasn't an e in the problem, it helped me bring down exponents. So if I do it here, I'll get this lowercase kind of curly L of lambda. This product here is going to turn into a sum, and I'll bring the exponents down. I get n times the log of lambda minus lambda, sum of the xi. So I'm going to take a derivative with respect to lambda, and I get n over lambda, and then this is just a constant times lambda, and I'm just going to get the constant. It's like the derivative of 3x with respect to x is 3. Then I'm going to set this equal to 0 and solve for lambda. So I'll do this one a little more carefully. Then 1 over lambda equals the sum of the xi over n, which is x bar. And then lambda is n over the sum of the xi. And then the actual estimator, the MLE, that's all just algebra. The MLE for lambda is lambda hat equals n over the sum as I goes from 1 to n of the capital Xi. This is a random variable. This is not lambda, which is a constant, but a random variable that we're going to use that will give different values with each sample, but is going to be what we're using to estimate the constant. And this, of course, is 1 over x bar. It's the same thing that we got for the method of moments estimator for the exponential. And a little red flag should be popping up. This is the biased estimator. So I did kind of start our maximum likelihood estimation discussion with this is a much better estimator than method of moments, not because it's unbiased, because that's not one of the properties. But we will see under very mild conditions for the underlying PDF that maximum likelihood estimators are always asymptotically unbiased, and that they also have a lot of good finite sample properties. So there's another MLE. We've used this estimator several times now. We've used it as a common sense, feel good kind of estimator, and it was method of moments, and now it's an MLE. Okay. I wanted to now go to a different kind of example, like specifically a two-parameter example, and then an example when the parameter is in the indicator, which causes you to have to think just a little bit more. But I realize I'm making this look like everything has to be continuous. So we haven't done a discrete distribution in a long time. Let's throw one in. Suppose that x1 through xn are IID from the geometric distribution. Now we have two geometric distributions, one that starts from 0 and one that starts from 1. Usually people write geom and then the parameter, which is usually the letter P. And then you have to figure out, do they mean starting from 0 or starting from 1 based on the context of the problem. I'm going to be specific here, though, and say the geometric that starts from 1. So the PDF, f of x and p. Oh, you know what? I did a discrete example of the Bernoulli, but this is going to be quick, so let's just finish this off. This is 1 minus p to the x minus 1 times p times an indicator, 1, 2, 3 on up for each xi. So because I already did the discrete example, I don't really need to do this. I'm going to do this a little faster. The joint PDF, f of the vector x and p, you're going to get by multiplying a bunch of these together. You're going to get 1 minus p to the sum of the x's minus n. Imagine multiplying a constant with x1 minus 1 and then the constant with x2 minus 1. You're going to add the exponents. You're going to get x1 minus 1 plus x2 minus 1. So you're going to end up with the sum of the two x's and then a minus 2. That's why I'm getting the minus n, if anyone was wondering. I'm going to get p to the n and a product of indicators, which is going to end up going away. You can see where the problem is going to come from. When the parameter is in the indicator, we're not just going to be able to drop this part, so we're going to have to deal with it. But if the parameter is not in the indicator, you generally don't have to worry about even writing that down. So maximizing this as a function of p, you could take a derivative with respect to p. Let's define a likelihood. I'm going to call this L of P, and I'm going to drop any constants of proportionality when thinking of this as a function of P, and I could drop those indicators because they were constant with respect to P. I think it's going to be easiest to maximize this by looking at the log. That is not always true. It is almost always true for us, but one day it will not be true, and you're going to take the log because it's going to be so ingrained in you. Just remember, if it doesn't make it easier, don't take the log. So this lowercase L of P is going to be the sum of the xi minus n times the log of 1 minus P plus n times the log of P. And then I'm going to take a derivative with respect to P. The derivative of this looks so much like what we already did in the Bernoulli case. I really regret starting this. This derivative is -1 over 1 minus P. So we get negative the sum of the xi minus n over 1 minus p plus n over p, and we set that equal to 0. And if I multiply both sides by p1 minus p, then I get the negative sum of the xi. Then I get negative p sum of the xi minus n plus n 1 minus p equals 0. And I get negative p sum of the xi plus np plus n minus np equals 0. We get cancellation. And you can see that if you solve for p, move things around, finish the algebra, make everything positive and put a hat on it, the MLE is the sum as I goes from 1 to n of the capital Xi over n, which is again x bar. So there is a maximum likelihood estimator for one of our two geometric distributions. Okay, kind of a waste of an example because I wanted to do something discrete and forgot that I already had. Let's go to a two-parameter example. So suppose we have a random sample x1 through xn, IID, from a normal distribution with mean mu and variance sigma squared, and let's assume they're both unknown. Because if one of them is known, then it's a one-parameter example. Let's find maximum likelihood estimators for mu and sigma squared. Same thing. I'm going to write down the PDF. F of x semicolon mu comma sigma squared is 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x minus mu squared. And I generally don't write an indicator with the normal because it would be like multiplying by 1 no matter what, because the indicator lets x go all the way from minus infinity to infinity. So the joint PDF is f of the vector x and mu and sigma squared. And because things are IID, we're going to multiply a bunch of the same PDFs over and over again, but with different x's plugged in. And I am going to go straight for, I'm going to write my coefficient like this, and I'll tell you how I got it. This is the most common way you're going to see this written. So in terms of the coefficient, a square root is a 1/2 power. You can write that fraction, you can put it all on one line by writing it as a negative power. So we've got like 2 pi sigma squared to the negative 1/2. And then we have n of them. So if you take something to the negative 1/2 and then raise that to the n, power up to a power, you get to multiply the exponents. So that's how I got 2 pi sigma squared to the negative n over 2. And then multiplying all those e's out, I'll get e to the negative 1 over 2 sigma squared, sum of the xi minus mu squared. So there's the joint PDF. And A, likelihood, you can always just take the joint PDF. Let's see what would happen. I'm gonna drop a constant. I don't have to drop this, and I'll show you where it would have gone. So if I break this up into 2 pi to the minus n over 2 and sigma squared to the minus n over 2, I can drop this, and the likelihood is going to be the rest of this. Let's suppose I don't drop it, though. I'm going to say capital L of mu and sigma squared is 2 pi sigma squared to the minus n over 2 e to the negative 1 over blah, blah, blah. What's next? The next thing is to maximize it any way you can. And it's almost always easier to take a log. So let's look at the log likelihood. I'm going to call this lowercase kind of script L of mu and sigma squared. This product is going to turn into a sum. I'm going to take the log of the first term and bring the exponent down. 2 pi sigma squared plus the log of the second term, and the e and the log are going to cancel, so I'll get minus 1 over 2 sigma squared. So I want to maximize this with respect to mu and sigma squared, and that means we're going to have to take a couple of derivatives. So first I'm going to take the partial derivative with respect to mu. The first term has nothing with mu in it. That part's going to be 0. The second term, I'm going to go in here and do a chain rule kind of thing. And that is going to be, the derivative will pass through the sum. I'll bring the 2 down. I'll get the xi minus mu sitting there to the first power, and then I'll multiply by the derivative of the inside with respect to mu, which is going to be negative 1. I'm going to end up with positive 1 over sigma squared, the sum xi minus mu to the first power. I'm going to set this equal to 0. And let's look at the other partial derivative with respect to sigma squared. So, oops. I've said several times in this course that I like to think of sigma squared as a symbol. I am going to take the derivative with respect to sigma squared, not with respect to sigma. So, be careful about what you're doing with those exponents. But looking at this, I have this negative n over 2 sitting here. The derivative of this with respect to sigma squared is the derivative of the argument inside. And with respect to sigma squared, that's just the constant 2 pi over the argument inside. You can see that that 2 pi is going to cancel and not be a part of this problem. That's the same reason it could have been canceled back here. it doesn't end up mattering. But continuing, the derivative of this. So I have a minus and I have a sigma squared in the denominator. So like a 1 over sigma squared, which is like a sigma squared to the -1. And the derivative with respect to sigma squared of sigma squared to the -1 is going to be -1 times sigma squared to the -2. So when I do that up here, I'm going to get a negative, which is going to turn this positive, and I'm going to get 1 over 2 sigma squared squared, which again is sigma to the 4th, but I personally like to keep it looking like a function of sigma squared, not a function of sigma. So let me get this out of the way. I am going to set this all equal to 0, and then I want to solve this system of two equations simultaneously. This probably means substituting one into the other, but actually for this problem it doesn't, because if you look at the first equation up here, this thing is equal to 0 if and only if this part in here is 0. So the sigma squared in the denominator, there's nothing you can put in a denominator that's going to make that 0. So the positive 1 over sigma squared, or negative, it doesn't matter, sum of the xi minus mu equals 0 implies that the sum of xi minus mu is 0, and this implies that the sum of the xi minus running the sum across n times mu is 0. And so if you solve for mu, you're going to get, and it's lowercase still while I'm doing the algebra, x bar. I could actually solve for mu using the partial derivative with respect to mu alone. That's not always possible. Once you have both your derivatives or three different partial derivatives, if you have three parameters, you want to solve that system of equations simultaneously. In this case, it turned out that we could solve for one of the parameters with one of the equations. And then I want to plug it in here. I want to do my cancellation. Let me simplify this a little bit. I could I could drop the 2's everywhere, which would basically be multiplying the left and right side of the equation by 0. I could multiply all the way across by this denominator, sigma squared. So if I multiply, sigma squared squared. If I multiply all the way across by sigma squared squared, and while I'm at it, let's just do the 2, then if I do that to both sides, I'll be left with negative n. And let's say I already canceled this. Sorry, I'm not writing this very well. I will end up with just a sigma squared because one of these is going to cancel with this. For the second term, everything's going to cancel, right? This is the denominator of down here. And I'll get the sum of the xi minus mu squared equals 0. So that's equivalent to the equation that is now at the top of the board. And I'm solving the system simultaneously, and I already have a solution for this. So if I plug that in, I'll get negative sigma squared plus the sum of the xi minus x bar squared equals 0 because mu is x bar. And if I solve for sigma squared, I will get the sum of the xi minus x bar squared over n. Now I'm at the end. Let's come up with the estimators. That was pure algebra. Let's put hats on things and make things positive. The sample mean is the MLE for the mu parameter for the normal distribution. And the MLE for sigma squared is the sum as I goes from 1 to n of capital Xi minus x bar squared over n, which is almost the sample variance, but it's the biased version because it's not divided by n minus 1. So here's another example of an MLE being biased, right? This is, if you care, this is n minus 1 over n times our sample variance. Some books would say it is the sample variance because some people define it to be that biased version. With two parameters, you're going to want to look at, some second derivatives, um, like a Hessian, and make sure you didn't minimize the likelihood or find a saddle point. Definitely do this in your research or your job, but I will warn you in one of my homework problems or exam problems if you should actually worry about that. So you can verify that we did maximize the likelihood. And in all these examples, we had a unique maximum. I think I can fit one more in, hopefully. Let's do this real fast. So that was our two parameter example. This is an example of the parameter in the indicator. Suppose that I have x1 through xn, IID, uniform 0 theta. And I want to find the maximum likelihood estimator for theta. So same thing, write down the PDF. The PDF here is 1 over theta, and that is on the interval from 0 to theta for x. That's our nice flat line distribution. You could close the endpoints of that interval. It doesn't matter. The joint PDF, I'm going to call f of the vector x and theta. It's going to be, because these are IID, the product as I goes from 1 to n of f of xi and theta, which is going to be 1 over theta to the n, and a product as I goes from 1 to n of these indicators. So the likelihood, or a likelihood, is L of theta, and that is 1 over theta to the n times a product of indicators. I can't drop them because it's not constant with respect to theta. I could rewrite this if I want, maybe to involve less x's. I don't have to do this, but I could rewrite this and I could say that the minimum has to be between 0 and theta, so x1 in parentheses, and the maximum has to be between 0 and theta. And that product of two things is actually equivalent to this product of n things. I could even write it like this. We did this, I think, way back at the beginning of class. I could say that the maximum is between 0 and theta, and the minimum is between 0 and the maximum. And if I did it that way, then this is constant with respect to theta, and I could drop it. So I could say my likelihood is 1 over theta to the n times just one indicator. But no matter how you write it, your indicator is going to involve the parameter and can't be dropped from the likelihood. So how do we maximize this as a function of theta? My advice to you is going to be to keep this sort of on the side. Like, I am going to drop it, but I'm going to keep it in mind because I really can't be dropping it. I'm going to look at this function. You can maximize this directly or look at the log of it. This is negative n log theta. If you take the derivative of this with respect to theta, you get negative n over theta. If you set this equal to 0, you are in trouble. Not only is there no information about the x's left, but this fraction can't be 0. Our sample size is always 1 or larger, and you can't make the denominator such that this is 0. There's basically no info here about the parameter. Like, what? You can't go any further, it seems. But then you remember, what was I trying to do? I'm trying to maximize this function. So let's look at it a little more carefully. L of theta, like, the goal hasn't changed. You want to maximize it, but the derivative didn't work. But if you look at the likelihood, you note that this is a decreasing function of theta. So if we want to maximize it, we want theta as small as possible. The parameter space for the uniform 0 theta is 0 to infinity. So you might think, well, I'm going to take theta to be 0, but remember the indicator that we're sort of keeping on the side. No matter which collection of indicators you used, here's what's happening. You've got your data, and theta is somewhere here, and you want it to be as small as possible given that you've observed the data. So could you put it here? Yeah, but you can make it smaller, smaller, smaller. The smallest possible theta given the data is actually the maximum value in the data. So given the data, the smallest possible theta is the maximum, i.e., the maximum likelihood estimator for theta for the uniform 0 theta distribution is theta hat equals capital X sub n maximum. So if parameter is in the indicator, this kind of thing is almost always going to happen. Maybe always, almost always going to happen. You're going to take a derivative and be like, I can't maximize this. But what's happening is, like in calculus, rather than having a function that has a maximum, you have something that's increasing or decreasing, in which case the maximum occurs at one endpoint. And the endpoint is defined in terms of the parameters. So that's how you get information about the parameter. So we'll do more examples next time, and we'll mix some of these. We'll look at multiple parameters where some of them are in the indicator, and then we will launch into a whole bunch of great properties involving MLEs. So I hope to see you next time in mathematical statistics.